September 25th, the year 2000. About 100,000 people watched the Sydney Olympics tracks event. An Indigenous female runner, Kathy Freeman, ran 400-meter final in 49.11 seconds. I think she broke the world record. She was also one of the first Indigenous athletes. So that was a big deal for us. So yeah. Nowadays, like it's sort of nice to see a lot more different people represented at the Olympic Games. This year there was a lot of refugees represented. There were a lot of there was trans representation. There was other LGBT representation. There was representation of even small countries. Yeah, it was kind of I don't know. The Olympic Games were pretty good this year. I thought so, at least. Mind you, they're struggling to remain relevant in the year 2021. So yeah. Anyway, let's get to the point. Lesson 49, creating constraints. We'll be able to create inequalities from two variables. Now, this is the reason I've written the learning goal like this is because we've actually been creating inequalities from one variable for a while. And now we've seen how to plot these inequalities when I've given you two variables. That was the big thing for 12E and 12E essentially. So what I want to do now is I want to take a step back and I want to say, okay, cool. Now that we can do that, how can we do this from worded examples? And I've got some worded examples here that I would like to go through today. Before I go through that, what did we do last lesson? Last lesson, which was yesterday, we were talking about this new terminology, which is called the objective function. An objective function is what you're trying to get to. It's an objective, what you're trying to solve. Usually for an objective objective, you can minimize or maximize something. So then what we did was, like, for example, an objective company for a burger shop, you might be wanting to try to maximize your profit. So you want to minimize your costs. So then what we did is we said, well, here are some suggestions of your objective function could be based on one of your costs would be staff. So how can you minimize this number? How can you make sure that C is as small as possible without, making your whole store go completely bankrupt? So therefore we said, even though we want to make C as small as possible, we have to have a certain number of managers and a certain number of team members. I said the maximum minimums of the objective function occur at the corners of the feasible region. So this corner here, this corner here, this corner here, and this corner here. But note, it only includes corners, no dotted line. So this one and this one wouldn't count because they've got a dotted line. So even though they go up, it's, because they've got a dotted line, they don't actually count as proper corners to the objective function. So what that means is you don't need to do the corner point principle on those corners because they don't count. Now, next. Then what we did is we talked about the feasible region, we did an example, and then we found the corners of the objective function for this one. Now, what we're going to do today is we're going to say, well, the next step for us would be to then create, to do the big questions that we would see in 12G. But to get to that, what I want to do is I want to say this. And the goal is going to be for today is this. These are the constraints on the feasible region. Now here I've given you the constraints. I've said X is greater than 0, Y is greater than 0, blah, blah, blah. What if I didn't give them to you? How would you create these? And that's going to be today's goal. So firstly, what we're going to do is I'm going to put up this. We're going to say, what is a constraint? Constraints are inequalities that limit the feasible region. What they do is they stop the feasible region from being as large as possible. And so this might be as simple as X is greater than 0, Y is greater than 0. And so, yeah. So, and what we're going to do for this example is we're going to start with a zoo enclosure. And what I'm going to do, so I'm just going to change one little thing about this slide. Give me a second. We're going to do this. Okay, we're going to do this. Okay, here we go. And I'm going to use, we're going to use to do an example for constraints is we're going to start with, we're going to look at a zoo enclosure. And this zoo enclosure has two types of animals. It has zebras and it has antelopes. And we're going to look at some possible like constraints that might be. So if you thought about this thing, you could have, as at the moment, we haven't put any constraints on this system at all. So you could have as many or as few antelope or zebra as you want. It could be just, you know, hundreds of millions, or it could be like 2 or 3. The first basic limitation that I would put on this example is I would say this. The first basic limitation is I would say the amount of, first what we're going to do is we're going to say Z equals zebra and A equals antelope. Now, the first limitation that I'm going to say is that you can't have negative zebras. Your enclosure can have 0 zebras. Your enclosure can have 20 zebras, but you can't have -5 zebras. So the first limitation, and this is actually a limitation that's going to show up in many of your questions, is going to be this. Z must be greater than or equal to 0. And antelopes must be greater than or equal to 0. These are 2 constraints. You are now saying that the number of antelope has to be greater than 0 or equal to 0. You can't have -5 antelope. And that might seem obvious to you guys, but you know, and yeah, duh, but there are some situations where you can have negative. If we were looking at temperature, then we wouldn't bind temperature like this. We wouldn't say T must be greater than or equal to 0 because it's like, well, you can have negative temperature. If we were talking about sea level, you can have negative, like you can go 1 meter below sea level, so you can have, so that would not be a negative. You could have a negative there. But like the things like antelope, people, pepperoni slices, time, fuel, you can't have negative of those things. So this is usually an easy starting place to start. These are 2 constraints that fix our position. Underneath that, we've got some extra constraints. It says the amount of antelope cannot exceed 10. Well, what might that look? Can I get a suggestion in chat or out loud? What might that look like? What might that inequality look like? The amount of antelope can't exceed 10. What might that look like as an inequality? Suggestions? The amount of antelope cannot exceed 10. Thank you, James Mia. Yep, A must be less than or equal to 10. And there must be at least 1 zebra. How could I do that one? And there must be at least 1 zebra. What would that one look like? Z must be greater than or equal to 1. Perfect. Now it's interesting here that I've already got, firstly, these are all I'm going to do these. These are all single variable. We're going to get single variable. What's the word? These are single variable constraints. All of these constraints just have one variable, either A or Z. It's interesting now that you've actually got two variables for Z. In fact, this variable down the bottom pretty much eliminates that variable there, but we're not going to focus on that. We've also now got an upper bound and a lower bound for A. So we could actually rewrite, if we wanted to, we could rewrite A and say A must be less than or equal to 10, but greater than or equal to 0. So that's another way we could write A. But you don't need to know that. I'm just saying though that these are all single variable constraints. So we're only looking at one variable in each of these. And how you figure them out is by looking at some of the terms here. By looking at the amount of animal cannot exceed, that means it can equal 10, but it can't go more than 10. It can't go past 10. So that's why we said equal to. It must be at least. That means it means more than or could be as low as 1. If it said there must be more than one zebra, then it would be Z is greater than 1. So we're going to see questions like that in a second. But yeah, those are the single variable constraints. What would it look like for double variable constraints or two variable constraints? I'm going to change the slide now, unless there's anyone here that objects. 5, 4, 3, 2, 1. Okay, there's no objections, so we're going to change the slide. We're going to look at now the same question, but now we're going to look at these two examples here. The total number of animals can't exceed 15. Whoops, I put that comma in the wrong place. Now, this one's been interesting. So now we're not looking at the amount of zebras, we're not looking at the amount of antelope, we're looking at the total number of animals. Now you will see this pop up in a lot of questions. The total number of staff, the total number of people. So just keep aware of how to do a question when it says the total. And if I say the total amount of animals, what that means is that what that would mean is that, well, the total amount is all of the zebra plus all of the antelope. If I took all of the zebra and I added all the antelope, that would give me the total amount of animals. And I know that the total amount of animals can't exceed 15. So now I know there is a cap on the total amount of animals. This is also our first constraint which uses both variables. Okay, so now I know if Z is 10, then A can't be 6. And I know if A is 8, then Z can't be 8 as well. There are certain values that Z can be that force A to be something different. And we're going to do another one. There must be more than 2 animals in the enclosure. So that's going to be very similar. Let me open up chat. What's that bottom one going to look like? There must be more than 2 animals in the enclosure. What is that constraint going to look like? Good. Z plus A must be greater than 2. Now, this is interesting, this one. So this one here is Z, Z plus A must be greater than 2. Now, this is a greater than. And yeah, because we're talking about animals here, we're talking about adding them. We don't care about what the type of animal is. We just know that they have to be there. And one of the other interesting ideas here is we've got this term here, more. So rather than saying more than or equal to, we've just said more. So that means you can't actually have 2 animals in the enclosure. You have to have more than 2. So that means you could have 3 or 4 or 5 animals. You can have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 animals. You can't have, so that means there's a limit. So that means we can have between 3 and 15 animals in the enclosure. So that gives us a bit of an idea, again, of some of the constraints. But then again, we also have to remember, if we were looking at this, we'd have to factor in these previous constraints. So we have to make sure that there is at least 1 zebra. So Z can't be 1. So therefore, you know, Z has to be 1 or more. So Z can't be 0. So you can't have an enclosure of just all antelope. You could have an enclosure at the moment. It says you could have an enclosure of just all zebras. So that's interesting. We're going to do, so these are constraints that I like to, these are constraints that refer to the total. So they refer to the total, and also the other way is these are 2 variable constraints. Now what we're doing is we're starting to close down our feasible region. At this point here, we'd have enough to get a feasible region that has 4 points, 4 quadrants in it. So that's pretty good. So that'd be interesting. But we're going to do 2 more constraints just to look at what 2 more constraints might look like. And these constraints, these last 2, are a bit different. These ones are relationship constraints. I'm making these terms up. What do you mean you're making these terms up? I'm literally making these terms up because, like, I don't think there is a name for them, but yeah. So don't look at these and be like, oh man, these are for relationship constraints. Tell your friends, and then they go, what the hell? But I'm trying to give them relevant names so that you guys can be like, oh yeah, that makes sense. Now, a relationship constraint is going to link one variable to the other. These are also 2 variable constraints. Might be like, why did I call them relationship constraints? When you get to a certain level of mathematics, you can start naming stuff whatever you want. As long as it makes sense, that's fine. I think that it'll make sense in this example. There can't be more than double the amount. So there can be double the amount, but there can't be more than double the amount of antelope compared to zebra. So this is actually there can't be more. So that means it's less than or equal to. So the amount of antelope can be, so there can't be more antelope compared to zebra. Now this is actually relying on one of the ideas that we learned when we talked about linear graphs. So not linear graphs, algebra, where we were like dealing with like, oh, a pencil is 3 times the price of, a book is 3 times the price of a pencil. So this is that same sort of idea which we struggled with back in the day. So we know that the antelope can be double the amount of zebra, but it can't be more than the amount of zebra. How do we know that? Because the can't be more than double the amount of antelope compared to zebra. So there can be. So the idea is that if I took the amount of zebras and I doubled that 2 times the amount of zebras, then that is the highest the antelope can be, right? The antelope can't be more than that. You can't have like 2 zebras and you can't have 2 zebras and 5 antelope. So the amount of antelope must be either equal to that value or less than, right? So therefore, that's how this inequality looks. This is probably one of the hardest inequalities that I've given you guys to think about. But, and then whenever I get a difficult problem, I like to just to see if this works. So let's take a couple of examples here. Let's say Z equals 2 and A equals 2. That should be okay. If Z equals 2 and A equals 3, that should be okay. If Z equals 2 and A equals 5, 2 times 2 is 4, so that should be not okay. Let's check our example here. Is 2Z greater than or equal to A? In this case, 2 times 2 is 4. Is 4 greater than 2? Yes. 2 times 2 is 4. Is 4 greater than 3? Yes. 2 times 2 is 4. Is 4 greater than 5? No. So it doesn't work. So that's what the expression looks like. I always suggest that to a student to do, especially like whenever you get a question like this, is to spend 20 seconds doing a couple of quick examples. You know, you don't even have to write them down. Just do them in your head if you can. But the idea is it's always good to check these because this is where students make little mistakes and then that might ruin the whole rest of the project. Now, the last one, there must be two more antelope for every zebra. Okay, that's actually wrong. There must be let me fix this. Oh man, I have to discard this. That's annoying. I'm gonna do this. There must be at least. There we go. Because that wasn't an inequality, that was an equals for a second. Now it's an inequality. What time have I got? Okay. So this one here was 2Z must be greater than or equal to A. So this one, there must be at least 2 more antelope for each zebra. So that means if I've got a zebra, there must be the amount of antelope must be, sorry, the amount of antelope must be, if I take the amount of zebras and add 2. So there must be at least that many. So they can be equal to that many or more than that many antelope. So that gives me another limit to the amount of to the value of A. So that sort of says to me there's a limit to how big A can be, but ultimately A needs to be bigger than Z. And those two sort of constraints still work. If Z is 2, then A can be 4. And that still works with the question above. If A is 3, then if Z is 3, then A can be 5. It still works because if you've got 3 and 5, 2 times 3 is 6, then that still works as well. So it even gets easier when you get higher numbers. And so that's the third type of constraint. And as I said, I refer to these ones as relationship constraints because they're linking one thing to another. And these are the hardest ones to do, in my opinion, because they require you to check. I would also constantly be checking these. Okay, so if the Z was equal to 3, then I would have A would have to be greater than or equal to 5. Does that make sense? Yes, that does make sense. If A was equal to 5, then that would work. If A was 7, then it would break this top one, actually. But yeah, we don't care about that. And so what you would do is you would take all of those constraints and put them together to get a feasible region. But one thing that might be annoying is that let's just say you do all this effort to get this feasible region and then like, well, okay, what about the objective function? What is our objective function? Let's pretend that this is our objective function. Let's say we've got, if feeding the zebras for a day, let's say you need 10 kilograms of food to feed the zebra. And feeding an antelope needs 8 kilograms. Create an objective function. I want you guys to copy this down, and I'd like you to suggest to me an objective function. What would the objective function be for the amount of food to be fed to the animals? And suggest it in chat, of course. Oops, sorry. Yep, okay. And good suggestion, Caitlin, you the type of variable. F, whoopsies. The objective function here would be F equals 10Z plus 8A. And that's this function here calculates the amount of food. So if I have 10 zebras and 1 antelope, then I'm looking at 108 kilos. And so what you might use this function for is to then go, okay, cool. So now what I can do is I can then say, well, we would want to probably maximize. We would probably want to maximize this function. Why? Because we want to get as many animals as we can. You might want to minimize this function. Like, okay, how can I make sure that I spend as little money on food? So that would be equal to the most animals. You might want to minimize this because you're a bad zoo owner and you want to actually, if you minimize this function, then that would give you the cheapest option. But that might be fine. You might be having, oh, now, listen, we want our zoo to have animals, but we can't afford that much money because, you know, costs and everything. So, you know, that's fine. But yeah. And yeah, so that's pretty much all. I'm trying to see what this would actually look like because I didn't actually do this, by the way. And then the other two would be very difficult to plot. 2Z must be greater than A, so that would be that'd be something like this. Like that one. Something like that, and then that will cross out this section here. I'm just being a bit nerdy over here, guys. I can sort of stop that. That would be 2Z must be greater than. Okay, and then yeah, so on and so forth. So you could use this to then figure out, well, what is the feasible region? The feasible region looks to me to be about here. And then you would then, once you had the feasible region, you could then use that to go and calculate the other ones. So that's actually going to be really tight. It's going to look something like this, I think. I think the feasible region is actually going to be here, but I'm not too sure.